And this was that situation I had mentioned earlier. Watch out for the fact that if you are given the Kb and you take the negative log of the Kb, that will give you the pKb. But the pKb is not the pKa. Let's go ahead and take a look at the details of question 2. Welcome to AP Chemistry Review and Practice. My name is Michael Farabaugh, and I'll be your guide on the side as you strive toward that 5 on the AP Chemistry exam. Each episode will include answers and explanations to practice problems, along with advice to help you avoid common mistakes. So, are you ready to review and practice for the AP Chemistry exam? I hope so, because this lesson starts right now. Welcome back to AP Chemistry Review and Practice. In this lesson, I'll give you the chance to review and practice topics 8.9 to 8.11. As you can see on this slide, these topics fall under Unit 8 in the AP Chemistry curriculum, Acids and Bases. You can add your comments and questions below this video, and you can also email me with your comments and questions at apchemistryreviewandpractice@gmail.com. Check out the links in the video description area, which include the link to the packet that accompanies this video. Now let's move on to the review for topic 8.9, Henderson-Hasselbalch equation. Here is an essential knowledge statement from the AP Chemistry course and exam description. The pH of the buffer is related to the pKa of the acid and the concentration ratio of the conjugate acid-base pair. This relation is a consequence of the equilibrium expression associated with the ionization of a weak acid and is described by the Henderson-Hasselbalch equation. Adding small amounts of acid or base to a buffered solution does not significantly change the ratio of concentration of A-, or the conjugate base, divided by concentration of HA, or the weak acid, and thus does not significantly change the solution pH. The change in pH on addition of acid or base to a buffered solution is therefore much less than it would have been in the absence of the buffer. So you can see on the bottom of this slide, that is the Henderson-Hasselbalch equation, and you can find it in the bottom of the equilibrium section of the AP Chemistry equations and constant sheet. And what I'd like to do is to do a little compare and contrast on this slide. So this is the Henderson-Hasselbalch equation. So pH equals pKa plus the log of the ratio of A- divided by HA. And again, those are concentrations of those two substances. So there is a specific example of a weak acid. So instead of HA, I'm showing you hydrofluoric acid, which has the chemical formula HF. And then you can see F- on the right side of the equation. That would be the conjugate base of hydrofluoric acid, HF. So now I'm going to write the Henderson-Hasselbalch equation, substituting F- for A- and substituting HF for HA. Now, if we were given the Ka value for hydrofluoric acid, which happens to be 6.8 times 10 to the negative 4, then the pKa value is the negative log of the Ka value. So the negative log of 6.8 times 10 to the negative 4 is 3.17. So the pKa for hydrofluoric acid is 3.17. Now I'm going to contrast that with what happens if we have a weak base. So the weak base I'm using as an example is ammonia, or NH3. So on the other side of the equation, it says NH4+. NH3 is the base, NH4+ is the conjugate acid. So in the Henderson-Hasselbalch expression, it's still going to be that the weak base in this conjugate acid-base pair would go in the numerator of that ratio. So the capital B represents ammonia, and you can see I'm substituting NH3 for that capital B in the numerator, and then the ammonium ion, NH4+, is substituted for the conjugate acid, Hb+. Now, everything looks good at this point, but watch out what happens next. In the previous example on the left side of this slide, I gave you the Ka value for HF, and then we took the negative log of that Ka. So suppose in the AP Chemistry question you are given ammonia and ammonium as part of a buffer system. If they give you the Kb value for ammonia, and then you take the negative log of that, this is where the mistake might happen. A student might say that 4.74 represents the pKa, but that's not true. The 4.74, which is the negative log of the Kb, that actually represents the value of pKb, not the pKa. So what do we need to do now? Well, let's go back to the equation sheet, and I've highlighted that the pKw is equal to 14. That's the negative log of the Kw. And the pKw is equal to the sum of pKa plus pKb, which is 14. So 14 minus the pKb is equal to the pKa. So while the pKb of ammonia is 4.74, the pKa of the conjugate acid or the ammonium ion is actually 14 minus 4.74, and that's 9.26. Now, this particular situation will appear later in this lesson when we get to question 2. But I wanted to show you that you have to be careful if you're given a Kb as opposed to a Ka when using the Henderson-Hasselbalch equation. Now let's go ahead and move on to the practice for topic 8.9. This is question 1. In question 1, we are given an equation for the ionization of a weak acid. It says nitrous acid, which has the chemical formula HNO2, ionizes according to the equation shown above. And we can see that the Ka for nitrous acid is 4.0 times 10 to the negative 4. So if we know the value of Ka, then we can calculate the pKa. So part A says calculate the value of pKa for nitrous acid. We pick up our calculator and we do the negative log of 4 times 10 to the negative 4, and we get 3.40. So that's the pKa for nitrous acid. Now we have to talk about a buffer solution in part B. A chemist prepares a buffer solution by combining 100 milliliters of 0.40 molar sodium hydroxide, which is a strong base, with 100 milliliters of 1.0 molar nitrous acid, which is a weak acid. Assume that the volumes are additive. That just means that 100 plus 100 equals a total volume of 200 milliliters for this buffer solution. So to prepare a buffer solution, if you take a strong base and you react it with a weak acid, then you can get a combination of the weak acid and the conjugate base. That would be a combination of HNO2 and NO2 minus. And we're going to see HNO2 and NO2 minus on opposite sides of the equation in part I of part B. It says write the net ionic equation for the reaction between the weak acid, HNO2, and the strong base, sodium hydroxide, NaOH. Now, this net ionic equation, it actually goes back to an earlier topic in Unit 8. This is topic 8.4, acid-base reactions and buffers. So when a weak acid and a strong base are mixed, they react quantitatively in a reaction represented by the following equation. Ha represents the weak acid, hydroxide or OH minus represents the strong base, and then on the other side of the equation we get water and we get the conjugate base, A minus. So let's go ahead and look at the specific example here in part Bi. The weak acid has the chemical formula HNO2. Since sodium hydroxide is a strong base and the sodium ion will be a spectator ion that will be eliminated on opposite sides of this equation, then we just write the hydroxide ion. Again, the sodium ion would be a spectator ion that would be eliminated from both sides of this equation. On the right side of the equation, we have the conjugate base of HNO2, which is NO2 minus, and then we have water. So there's the answer to part Bi. Now, remember, this is about the Henderson-Hasselbalch equation. So in part B, double I, it says calculate the pH of this buffer solution. So we will use the Henderson-Hasselbalch equation to calculate the pH of this buffer solution. What I'd like to do now is to focus on the number of moles of HNO2 and the number of moles of sodium hydroxide, or the hydroxide ion. So to get number of moles, I will do volume times molarity. So there is 100 milliliters of a 1.0 molar solution of nitrous acid. 100 milliliters, if you divide by 1,000 to go from milliliters to liters, that is 0.1 liters. And then times the molarity as 1 mole per liter, that gives us 0.1 times 1, so 0.10 mole of nitrous acid. Now, with the hydroxide ion coming from sodium hydroxide, it's going to be, again, 100 milliliters, or 0.1 liter, times 0.40 moles per liter. So 0.1 times 0.4 is 0.04 moles of sodium hydroxide, or the hydroxide ion. Notice that this is not a 1-to-1 ratio. We are not doing an acid-base titration. We are actually not even considering the half equivalence point, but we are creating a buffer solution with a combination of the weak acid, HNO2, and the conjugate base, NO2-. Now, how many moles of HNO2 will we have after this reaction goes to completion? And how many moles of NO2- will we have after this reaction goes to completion? This sounds like a good job for making a rice table, which is what I did. So I have 0.1 mole of HNO2, the weak acid. I have 0.04 mole of the strong base, or the hydroxide ion, and we haven't produced any NO2- yet. So the majority of the chemicals before this reaction takes place are in the form of HNO2 and hydroxide. Let's go ahead and let the reaction proceed. So minus 0.04, minus 0.04, plus 0.04. Again, we have coefficients of 1, 1, and 1. And so now 0.1 minus 0.04 is 0.06 mole of nitrous acid after this reaction goes to completion. Let's assume that all of the hydroxide ion is consumed. And then we have produced 0.04 mole of nitrite ion, or NO2-, the conjugate base. Now, I know that these numbers are moles, but we can use these values in the Henderson-Hasselbalch equation. Take a look. We have our pKa in part A. We now have a net ionic equation in part B, and we understand the quantities of moles of both the weak acid and the conjugate base. The weak acid is HNO2. The conjugate base is NO2-. So here is our Henderson-Hasselbalch equation. NO2- is substituted for A-. HNO2 is substituted for HA, and I will put 0.04 in the numerator of that ratio and 0.06 in the denominator of that ratio. Now, you might be thinking, shouldn't those be concentrations and not moles? But since they are in the same solution, they're in the same total volume, then the ratio of the number of moles is the same as the ratio of their molarity values, or their concentrations. So the pKa is 3.40. We have the log of the ratio of 0.04 divided by 0.06, which again, I know that those are moles and not molarity values, but the ratio would be the same. And now when I do the math, I'm going to get a value for the pH of this buffer solution. Let's make a quick prediction. Do we have an equal amount of HNO2 and NO2-? No. If we did, then the log of 1 would be 0 and pH would equal pKa. Looks like we have slightly more of the HNO2 and slightly less of the NO2-. So this is topic 8.7, pH and pKa. If the acid form has a higher concentration than the base form, then the pH should be less than the pKa. And so that's my prediction, that I haven't picked up my calculator yet, but the pH should be less than the pKa for this buffer because the concentration of HNO2 is greater than the concentration of NO2-. Now, when I do pick up my calculator, it's going to be 3.4 plus the log of that ratio of 0.04 divided by 0.06. And when I do that math, I get 3.22, which is the prediction that the pH should be less than the pKa. So there are the answers to parts A and B of question 1. And now it's time to move on to question 2. And this was that situation I had mentioned earlier. Watch out for the fact that if you are given the KB and you take the negative log of the KB, that will give you the PKB. But the PKB is not the pKa. Let's go ahead and take a look at the details of question 2. In question 2, we see a diagram indicating a buffer solution. It says a buffer solution is prepared in a beaker as shown above. The concentration of the ammonia, which is the weak base, is 0.85 molar. And the concentration of the ammonium nitrate, which contains ammonium is the conjugate acid of ammonia, that is 0.65 molar. So we have concentration of a weak base, concentration of its conjugate acid. It says that the Kb value for NH3 or ammonia is 1.8 times 10 to the negative 5. Which of the following mathematical expressions can be used to determine the approximate pH of this buffer solution? So go back to what I had mentioned earlier in this lesson, that if you are given the Kb for a weak base, and you take the negative log of the Kb, that gives you the pKb, which is not the pKa. So 14 minus 4.74 is equal to 9.26. 9.26 is the pKa for the ammonium ion. 4.74 is the pKb for ammonia. So looking at the 4 answer choices, we can see that in choices A and B, they took the negative log of 1.8 times 10 to the negative 5. Well, that would be the pKb, and that would not be part of the Henderson-Hasselbalch equation, so we can go ahead and eliminate choices A and B. In choices C and D, they did 14 plus the log, and that's the same as 14 minus the negative log, and that would give us what we are looking for. In the Henderson-Hasselbalch equation, that's the pKa. So the correct answer to question 2 is not choices A or B, it's either choice C or D. Now, looking at the next part of the Henderson-Hasselbalch equation, there's that ratio. It's A minus over HA, or it's the concentration of B, the base, over the concentration of HB plus, the conjugate acid. And that's what we have here. The B represents ammonia, NH3, and the HB plus represents ammonium, NH4 plus. So there's my Henderson-Hasselbalch equation. I know that I'm looking at choices C or D. I want ammonia to be on top in that ratio, and I want ammonium to be on the bottom in that ratio. So it's going to be 0.85 over 0.65. And so that makes choice D the correct answer to question 2. All right, well, hopefully the answer to question 2 and my explanation of that calculation makes sense. Let's go ahead and take a look at question 3. Question 3 says the following. A student prepares a buffer solution by mixing 100 milliliters of 1 molar HF, which is hydrofluoric acid, that's a weak acid, with 100 milliliters of 1.1 molar NaF, or sodium fluoride. Now, the fluoride ion, or the F minus ion, that's the conjugate base of the weak acid HF, or hydrofluoric acid. So the pKa of hydrofluoric acid is 3.17. And the question asks, which of the following shows the correct values for both the ratio, that would be concentration of fluoride over concentration of hydrofluoric acid, and the pH of this solution. So we have the ratio and we have the pH. We can see 4 choices. We have a ratio of either 0.909 or 1.10, and then we have a pH of either 3.13 or 3.21. So this is our generic Henderson-Hasselbalch equation. I'm going to substitute F minus for A minus, and I'm going to substitute HF for HA. I'm also going to include 3.17 as the value of pKa. Now I'm going to take a look at moles like I did back in question 1 in this packet. So to calculate the number of moles of HF, I will do volume times molarity. And then similarly, to calculate the number of moles of the F minus, I will do volume times molarity. So volume times molarity, that would be 100 milliliters or 0.1 liter times 1 mole of HF per liter. That gives me 0.1 mole of HF. And then when I do volume times molarity for the sodium fluoride or the fluoride ion, I get 0.1 liter, so 100 milliliters, 0.1 liter, but now it's 1.1 mole per liter. So we can see that there's a slightly greater value of F minus than HF. Now, as I had mentioned earlier, even though what I'm putting into the Henderson-Hasselbalch equation is not concentration, but rather number of moles, the ratio of the number of moles is the same as the ratio of the molarity values. So hopefully you can see that 0.11 divided by 0.1 will give us a ratio that is greater than 1. So that ratio is not 0.909, that ratio is 1.1. So the correct answer to question 3, based on the ratio of concentration of F minus over concentration of HF, it's a 1.1 ratio. That's going to be choices C or D. Now, with respect to the pH, let's go ahead and make that prediction. So we can see that there should be a greater amount of F minus than HF in this buffer solution. And so if the base form has a higher concentration than the acid form, then the pH should be greater than the pKa, as we learned back in topic 8.7. So the pH greater than the pKa, that's my prediction, because the concentration of F minus is greater than the concentration of HF. So I'm fairly confident that the correct answer to question 3 will be choice D, because the pH should be greater than the pKa. But when I pick up my calculator and I do 3.17 plus the log of 1.1, then in fact that's what I do get on my calculator. I get 3.21. So the correct answer to question 3 is choice D. Okay, now it is time to move on to the review for our next topic. This is topic 8.10, buffer capacity. Here are some essential knowledge statements from the AP Chemistry course and exam description. Increasing the concentration of the buffer components while keeping the ratio of these concentrations constant keeps the pH of the buffer the same, but increases the capacity of the buffer to neutralize added acid or base. And when a buffer has more conjugate acid than base, it has a greater buffer capacity for the addition of added base than acid. So to kind of explain what that means, this is a generic weak acid, or HA, reacting with the added base, hydroxide. Now there's also a component of that buffer which is the conjugate base, or the A minus. So the A minus reacts with the hydronium ion, or H+, and that would be reacting with added acid. So now, looking at that essential knowledge statement that's highlighted on this slide, it says, when a buffer contains more conjugate acid than base, and so I'm increasing the font size to say, what if there's more HA than A minus? It would have a greater buffer capacity for the addition of added base than acid. And let's go the other direction with that last essential knowledge statement. What if the buffer has more conjugate base, or A minus, than acid? So I'm highlighting that with a larger font. It would have a greater buffer capacity for the addition of added acid than base. So these last two essential knowledge statements sound a little bit wordy and possibly confusing. So when we take a look at our next question in this packet, I think it will make a little bit more sense. So now it is time to move on to the practice for topic 8.10. This is question 4. Now, if you look at the 4 answer choices for question 4, you can see those same phrases that I was just mentioning. The idea of greater buffer capacity for the addition of added base than acid, or added acid than base. Let's go ahead and take a look at the details of question 4. It says information about 2 different buffer solutions is shown in the table above. So we can see solution 1, which contains a 1 molar solution of a weak acid and a 2 molar solution of the potassium salt that would be of the conjugate base. And then solution 2, there is a 2 molar solution of a weak acid and a 1 molar solution of the potassium salt of its conjugate base. Same volume for solution 1 and solution 2. Solution 1 has a pH of 5.04 and solution 2 has a pH of 8.91. So what I'd like to do next is focus on solution 1. Again, I can see that the acid component of the buffer, there's the formula of the weak acid, HC2H3O2. And so what does the acid component of the buffer do? It reacts with added base. Now, there's also the base component of the buffer, which is the conjugate base. So it's a conjugate acid-base pair. So the conjugate base is C2H3O2-. And what does the base component of the buffer do? It reacts with added acid. Now, we do not have an equal amount of number of moles of the acid and the base component. So what do we have more of? Well, I see 1 molar for the weak acid, and I see 2 molar for its conjugate base. So looking at that, I can say that for solution 1, it has a greater buffer capacity for added acid than base. Why? Because there are more moles of the base component of the buffer than there are moles of the acid component of the buffer. So I've just analyzed the details of solution 1. Let's go ahead and analyze the details of solution 2. So the acid component of the buffer is the weak acid, HCN. What does the acid component of the buffer do? It reacts with added base. And then we have the KCN, but that's really just the CN minus ion. So the base component of the buffer is CN minus. What does the base component of the buffer do? It reacts with added acid. And which concentration is present in a greater amount? Looks like there is more of the acid than there is the conjugate base. So that means for solution 2, this is the analysis. Solution 2 has a greater buffer capacity for added base than acid. Why? Because there are more moles of the acid component than there are moles of the base component. So now that I've shown you the analysis of solution 1 and solution 2, let's go back and look at question 4 and the 4 answer choices. Now, the first thing I'm going to do is eliminate 2 of these 4 choices because their justification is incorrect. So focus on the following phrases in choices A and C. Because the pH of the solution is less than 7, or because the pH of the solution is greater than 7, that is an incorrect justification. So the correct justification for this question is to compare the relative number of moles of the buffer components. So the buffer capacity for the addition of added acid or added base is not based on the pH of the solution. It is based on the relative number of moles of the buffer components. So let's go ahead and eliminate choices A and C. Now, focusing on choice D, and that is solution 2. Now, we know from our analysis that solution 2 has a greater buffer capacity for added base than acid. But that's not what it says in choice D. It says greater buffer capacity for the addition of added acid than base, and so that makes choice D incorrect. So we know that the correct answer to question 4 is choice B, and here's why. Solution 1 has a greater buffer capacity for added acid than base. Why? Because there are more moles of the C2H3O2-, which is the base component of the buffer, and so that makes it having a greater buffer capacity for added acid. So correct answer to question 4 is choice B. All right, well, hopefully the correct answer to question 4 and my explanation for that makes sense to you. Now it's time to move on to question 5. Question 5 gives us another example of a buffer solution. This time, the buffer solution contains the weak acid, hypochlorous acid, which has the chemical formula HClO, and then its conjugate base would be the ClO- ion. So here are the details of question 5. It says 2 solutions are prepared by combining hypochlorous acid, HClO, and Potassium hypochlorite, which has the chemical formula KClO, again the ClO minus, that's the conjugate base of the weak acid HClO. So details of the experiment are shown in the table below. Now we have solution 1, and we can see that 1 liter of 0.20 molar hypochlorous acid is combined with 1 liter of 0.20 molar potassium hypochlorite. Now what do you notice? A 1-to-1 ratio of the weak acid and the conjugate base, but a lower concentration. Whereas solution 2, it's a 1-to-1 ratio with a higher concentration. So not 0.20 molar, but rather 2 molar. So solution 2, same ratio of buffer components, but 10 times higher concentration. All right, part A of question 5 says the following. The value of Ka for hypochlorous acid, HClO, is 3.0 times 10 to the negative 8. Calculate the pH of solution 1. Now, when I use the Henderson-Hasselbalch equation to calculate the pH of solution 1, I realize that the ratio is a 1-to-1 ratio, and the log of the number 1 is actually 0. So here is my first attempt at calculating the pH. This is not the Henderson-Hasselbalch equation yet. This is just simply calculating the pKa for hypochlorous acid. So the negative log of 3.0 times 10 to the negative 8 is 7.52. Now, pH equals pKa plus the log of ClO minus concentration over HClO concentration, but that ratio is 1-to-1, and the log of 1 is 0. So pH equals pKa, and so therefore 7.52, that is the pH of solution 1. Now, if you anticipate what's going to happen with solution 2, you realize that it has the same 1-to-1 mole ratio of the weak acid and the conjugate base. So the question in part B says, is the pH of solution 2 less than, greater than, or equal to the pH of solution 1? Justify your answer. So one of the essential knowledge statements for topic 8.10 says that increasing the concentration of the buffer components, which we can see happening in this question, but while keeping the ratio of these concentrations constant, keeps the pH of the buffer the same. Now it does change the buffer capacity, but the pH of solution 2 is equal to the pH of solution 1. So each of these solutions contains equimolar amounts of the weak acid, HClO, and its conjugate base, ClO minus. So although solutions 1 and 2 have different buffer capacities, the pH of each solution should be the same. So pH equals pKa equals 7.52 for both solution 1 and solution 2. So what about the difference in buffer capacity? Well, let's go ahead and take a look at part C of question 5, and we can talk about buffer capacity. It says, a sample of 0.10 mole of solid sodium hydroxide is added to each solution. The solutions are thoroughly mixed. To dissolve all of the solid sodium hydroxide, assume that the change in volume of each solution is negligible. The pH of each solution is measured at the end of the experiment. So I believe that one of these buffers will do a better job of maintaining a more constant pH, and then the other buffer will not be able to keep the pH relatively constant. So that's the essence of a difference in buffer capacity. So part C says, which solution, 1 or 2, should experience a greater change in pH as a result of the addition of a 0.10 mole NaOH, or sodium hydroxide sample? Now we have to justify our prediction in terms of each of the following: the number of moles of the buffer components and the buffer capacity. Now what I'm showing you on this slide is that essential knowledge statement, but I'm underlining a different portion. So before I talked about how the pH of the buffer is the same, but again, increases the capacity of the buffer to neutralize added acid or base. That's when there are different concentrations of the buffer components. In my video for topics 8.6 to 8.11, and I include a link to that video in the video description area, I had presented this problem. So I'll talk about this particular problem, then we'll go back to look at question 5 after we examine this example. So in this example from that other video, you can see a 1 molar concentration for buffer number 1, and you can see a 0.0500 molar concentration for buffer 2. So buffer 1 clearly has a larger concentration of the buffer components. Buffer 2 has a smaller concentration of the buffer components. But notice that their initial pH is the same. It's 4.74. So what happened in that problem from that question in the video is that a sample of nitric acid, which is a strong acid, was added to a 1 liter sample of each buffer. Now, did each buffer have a decrease in pH? Yes, because nitric acid is a strong acid. But notice that buffer number 1 had a greater buffer capacity, and that explains why the pH changed by a smaller amount. It went from 4.74 to 4.70. Now, buffer number 2, with a smaller buffer capacity, its pH dropped all the way down to 3.47, so that explains why the pH changed by a greater amount. So to summarize, before we go back to question 5, greater buffer capacity, smaller change in pH when either a strong acid or a strong base is added, smaller buffer capacity, greater change in pH when a strong acid or a strong base is added. All right, now back to question 5. So solution 1 has a smaller buffer capacity and a greater change in pH. Solution 2 has a greater buffer capacity and a smaller change in pH. Now let's go ahead and read the question carefully. So it says, which solution, 1 or 2, should experience a greater change in pH as a result of the addition of the sodium hydroxide? So greater change in pH, that would be solution 1. Now I had to address both the number of moles of the buffer components and the buffer capacity. This is what I said. Solution 1 should experience a greater change in pH as a result of the addition of 0.1 mole of sodium hydroxide. Solution 1 has a smaller number of moles of the buffer components and a smaller buffer capacity. All right, well, hopefully my answers and explanations to question 5 make sense. Now it is time to move on to the review for our next topic. This is topic 8.11, pH and solubility. Here is an essential knowledge statement from the AP Chemistry course and exam description. The solubility of a salt is pH sensitive when one of the constituent ions is a weak acid, a weak base, or the hydroxide ion. And these effects can be understood qualitatively using Le Chatelier's principle. Now let's move on to the practice for topic 8.11. This is question 6. In question 6, we can see an equation for the dissolution of solid calcium hydroxide in water. So the solid calcium hydroxide dissolves in water to produce calcium ions and hydroxide ions, and we can see the KSP is 5.0 times 10 to the negative 6. Question 6 says the dissolution of calcium hydroxide is represented by the equation shown above. A chemist prepared a saturated solution of calcium hydroxide by adding excess solid calcium hydroxide to a test tube containing distilled water and stirring until no more solid dissolves, as shown in diagram 1 below. Then, the chemist adds a few drops of solution X to the test tube and observes that the solution turns cloudy, as shown in diagram 2 above. Now, the identity of solution X is either nitric acid, HNO3, or sodium hydroxide, NaOH. And based on the results of this experiment, which of the following indicates the correct comparison of the reaction quotient Q and the equilibrium constant KSP for this reaction when solution X is added to the test tube and correctly identifies solution X? So we have an equilibrium as shown in diagram 1, and then that equilibrium is disturbed by the addition of solution X as shown in diagram 2. So the solution turns cloudy, Now, this indicates that additional solid particles are formed when solution X is added. So that means that this equilibrium experiences a net conversion from right to left, or a net conversion from products to reactants. And so additional solid is formed, which is why the solution turns cloudy. Now, let's talk about the comparison of Q versus KSP in order for that to occur. So back in topic 7.7, we learned that when Q, the reaction quotient, is greater than K, the equilibrium constant, then there will be a net conversion from right to left, or a net consumption of products and generation of reactants. So we can say that when solution X is added, Q becomes greater than KSP. And so that's why the additional solid that was formed caused the solution to turn cloudy when solution X is added. Now that we know that Q becomes greater than KSP, we can eliminate choices A and B because they say that Q is less than KSP when solution X is added to the test tube. So the correct answer to question 6 is either choice C or D, which indicates that Q is greater than KSP when solution X is added to the test tube. Now, what is the identity of solution X? Is it nitric acid or sodium hydroxide? So if it were nitric acid, which is a strong acid would react with a strong base. In this case, the hydroxide ions would react with the hydronium ions or the H plus ions from the strong acid. So if the acid were added and the hydroxide ions reacted with it, this would cause the concentration of the hydroxide ions in that solution to decrease. And if the concentration of the hydroxide ions decreases, well, that would actually cause Q to become less than KSP. And the equilibrium would experience a net conversion from reactants to products. So this calcium hydroxide would actually become more soluble if we had added an acid to the test tube. But because this calcium hydroxide actually becomes less soluble, then it looks like choice D is going to be the correct answer. So the sodium hydroxide adds an additional source of hydroxide ions to the test tube. So this causes the concentration of the hydroxide ions to increase. And if the concentration of hydroxide increases, now Q becomes greater than KSP, and the equilibrium would experience a net conversion from right to left, or from products to reactants. So the correct answer to question 6 is choice D. So the solution X was sodium hydroxide, and this increased the concentration of hydroxide. Q became greater than KSP. The equilibrium shifted from products to reactants. Additional solid calcium hydroxide was formed, and that's why the solution turned cloudy. All right, well, that's the answer to question 6. Now it's time to move on to question 7, which also involves a saturated solution. This time, instead of calcium hydroxide, this is magnesium hydroxide. So we are given the equation for the dissolution of solid magnesium hydroxide. We are given the KSP value, and it says the dissolution of magnesium hydroxide is represented by the equation shown above. A student prepared a saturated solution of magnesium hydroxide by adding excess solid magnesium hydroxide to a beaker containing distilled water and stirring until no more solid dissolves, as shown in the diagram above. Then, the student adds several drops of concentrated nitric acid, HNO3, to the mixture in the beaker. Does the amount of undissolved magnesium hydroxide solid increase, decrease, or remain the same as the nitric acid is added? Justify your prediction with a comparison of Q and KSP. Hopefully you can tell that questions 6 and 7 are opposite to each other, in that in question 6, a sodium hydroxide solution was added, which caused the calcium hydroxide to become less soluble. But here in question 7, it looks like it's going to be nitric acid added, and that will make the magnesium hydroxide even more soluble. So a strong acid reacts with a strong base. So the strong acid H plus or hydronium reacts with the strong base hydroxide. So here comes the nitric acid to the mixture. The nitric acid contains H plus ions or hydronium ions, and they would react with the hydroxide ions in the mixture. And what will this do to the concentration of the hydroxide ions? It causes the value of the concentration of hydroxide to decrease. And if the concentration of hydroxide decreases, how will Q compare with KSP? Well, there will be a net conversion from left to right, or from reactants to products. So if the equilibrium experiences a net conversion from reactants to products, then that would mean if Q is less than K. So if Q becomes less than KSP, then there will be a net consumption of reactants and generation of products. So the equilibrium will experience a net conversion from left to right, from reactants to products, when the nitric acid is added. So Q becomes less than KSP. Now, more of the solid magnesium hydroxide will dissolve, and the amount of undissolved solid magnesium hydroxide will decrease in that mixture. So we add the acid, the H plus ions from the nitric acid react with the hydroxide ions, concentration of hydroxide decreases, Q becomes less than KSP, more solid magnesium hydroxide will dissolve, making the amount of undissolved solid magnesium hydroxide decrease. All right, let's go ahead and move on to our next question. This is question 8, and this is the last question in this packet. Question 8 says the following. The dissolution of silver cyanide, AgCN, in water is represented by the equation above, and the KSP for AgCN is 6.0 times 10 to the negative 17. The molar solubility of AgCN increases when it is dissolved in a 0.5 molar solution of nitric acid instead of neutral distilled water. So if the molar solubility of AgCN increases, then the equilibrium experiences a net conversion from left to right, from reactants to products. And the question asks, which of the following represents the balanced net ionic equation for the process that occurs between species in solution that contributes to the increased solubility of AgCN in a solution of nitric acid? So we have 4 choices, and there was a net conversion from left to right with magnesium hydroxide. This is a net conversion from left to right for silver cyanide. Now, in question 7, we justified our answer by stating that the H plus ions from the strong acid reacted with the hydroxide ions in the mixture. Here in question 8, we don't see any hydroxide ions in this equation. All we see is silver ions, Ag+, and cyanide ions, Cn-. So which ions present in the solution, the silver or the cyanide, are more likely to react with the H plus ions from the nitric acid? So I can see hydronium is featured as H3O+. You should know that H plus and hydronium are often used interchangeably. So let's go ahead and consider the 4 choices. Choice A involves the reverse of the reaction that we were given. But making more solid silver cyanide doesn't help to explain why this is becoming more soluble. So it doesn't explain the increased solubility in the presence of nitric acid. Now, choices B, C, and D all involve a hydronium ion reacting with something. And that's good. The hydronium ion would be present in a solution of that strong acid, nitric acid. But take a look at choice C. Again, making more of a solid compound doesn't help to explain the increased solubility. Also, that equation is not balanced. I see 3 H atoms on the left, and I see only 2 H atoms on the right. And I see a +1 on the left, and there's no charge on the right. So that's not balanced in terms of either atoms or charge. Let's go ahead and eliminate choices A and C for the formation of a solid and an incorrect equation. Now, I still see hydronium either reacting with Cn- or hydronium reacting with the nitrate ion. So the problem with choice D is that it doesn't involve the silver or the cyanide. And so if that equation doesn't involve silver or cyanide, then it doesn't explain why the silver cyanide becomes more soluble in the presence of the nitric acid. So we need the nitric acid or the hydronium ion to react with either silver or cyanide to indicate this shift in the equilibrium from left to right. So the correct answer to question 8 is choice B, and here's why. The nitric acid is added to that saturated solution of silver cyanide. The H+ ions from the nitric acid, that increases the solubility, and here's why. It reacts with the cyanide ions. This causes the value of the cyanide concentration to decrease. So in the presence of that acid, there will be a net conversion from reactants to products from left to right, and that makes the silver cyanide more soluble. Q becomes less than KSP, so more solid silver cyanide will dissolve, making it more soluble in the presence of a strong acid. So the correct answer to question 8 is choice B. And again, we can see that the H+ or the hydronium ions reacted with the cyanide ions, decreasing the concentration of cyanide, causing Q to become less than KSP, and shifting the equilibrium from left to right, making the silver cyanide more soluble in the presence of nitric acid. All right, well, that's the last question in this packet. So now it's time to move on to the part of the lesson where I give you advice to help you avoid common mistakes. So my first piece of advice for you is if you need more information on the topics that were presented in this lesson, then you can review the information in my video for topics 8.6 to 8.11, and there's a link to that video in the video description area. My next piece of advice is what I normally say during this part of the lesson. Read the question carefully and make sure you are answering the question that is being asked. Always show your work for your calculations, and when using the Henderson-Hasselbalch equation, take care to avoid calculation errors. So to show you some examples of calculation errors that other students have made on the AP Chemistry exam, I'm going to present 2 recent AP free response questions that deal with the Henderson-Hasselbalch equation. The first one is a free response question from the 2025 AP Chemistry exam. This is free response question number 2, part B, Roman numeral 3. In this question, we have an example of ascorbic acid, which is acting as a weak acid. We have a titration curve involving a 10 milliliter sample of this ascorbic acid solution, titrated with a 0.0550 molar solution of sodium hydroxide. Now we can see that the location of the equivalence point on this titration curve is located at 16 milliliters. So the first part of part B, it says calculate the molar concentration of the ascorbic acid solution. If we know the volume and the molarity of the sodium hydroxide, and then we know the volume of the ascorbic acid solution, we can set up a calculation to determine the concentration of the ascorbic acid solution. So there's the answer to that first part of the question from the official scoring guidelines. Now the next part was to determine the approximate pKa of ascorbic acid. And since pKa would be equal to pH at the half equivalence point, it looks like the pH is approximately 4.1 on this titration curve. So now that we know that the pKa is approximately 4.1, we can use that pKa value of 4.1 in the Henderson-Hasselbalch equation. So the last part of part B of question 2 from the 2025 AP Chemistry exam says, what is the ratio? What is the value of the ratio of concentration of the ascorbate ion, or the Asc- ion, over the ascorbic acid concentration? So that ratio is the A- over HA that you would normally see in the Henderson-Hasselbalch equation. And they say that the pH of the solution is 4.7. So I'm going to put 4.7 for the pH, and I'm going to put 4.1 for the pKa. So 4.1 for the pKa and 4.7 for the pH of the solution. Now 4.7 minus 4.1 is equal to 0.6. And you should know that if the log of a value is equal to a particular number, then 10 raised to the power of that number would give you the ratio. So in this case, the ratio of the concentration of the ascorbate ion over the concentration of ascorbic acid, that would equal 10 raised to the 0.6 power. And so when you do that math, you get 4. So 4 is the answer for that ratio, and you can see on the official scoring guidelines that the value of 4 and how they solved it is right there. Now, this is the part of the lesson where I give you advice to help you avoid common mistakes. So here are 3 examples of common mistakes that we observed at the AP reading for the 2025 AP Chemistry exam. So here's the first example of a mistake. So what students did wrong is instead of using 10 to the 0.6 to do that math, that calculation, they used natural log, or e to the x, which was the wrong operation on their calculator. Another error was instead of doing 10 to the 0.6, I think that perhaps students are so accustomed to doing 10 to the minus pH when solving for the concentration of H+, that they automatically put into their calculator 10 to the minus 0.6 instead of 10 to the 0.6, so they got the wrong answer for that reason. And then this is unfortunate. Several responses, they set up the calculation correctly using the Henderson-Hasselbalch equation, but then they stopped, and they did not actually solve for the ratio. So again, take care to avoid those types of mistakes. So continuing, this is another recent AP Chemistry exam. This is from 2024, and this is question number 2, part G. So part F of this question involved calculating the pKa for a particular weak acid. So the formula of the weak acid was HC4H2O4-, and that Ka value, as you can see highlighted, is 8.5 times 10 to the negative 7. Now that we figure out the pKa by taking the negative log of 8.5 times 10 to the negative 7, the pKa is 6.07, which we can use in the Henderson-Hasselbalch equation. Now, the buffer solution has a pH of 7. Well, let's go ahead and put 7 into the pH because the buffer solution has a pH of 7. What about the pKa? We've already calculated that. It's 6.07. So what's 7 minus 6.07? Well, that works out to be 0.93. Just like we saw in that previous question from the 2025 AP Chemistry exam, what students had to do is 10 raised to the power, and that would be 10 raised to the power of 0.93. So 10 raised to the power of 0.93 gives you 8.5, and that was the correct answer to part G of this question. So take care to avoid the following 4 examples of mistakes that were observed at the 2024 AP Chemistry reading. Some students saw that the pH was 7, and they made the incorrect assumption that, oh, the acid and the base are equal. But that is incorrect. This is not about H plus and OH minus and a neutral solution of water. So that was an incorrect assumption that that ratio would be 1 because the pH is 7. That ratio was actually 8.5, as I showed you. Another mistake was just a calculation error. So they had 10 to the negative 0.93, so they got the wrong answer. Or that they flipped the acid and the base in the Henderson-Hasselbalch equation. So because the ratio was upside down, they also got an incorrect value for the concentration. Instead of 8.5, they actually had the reciprocal of 8.5, which was incorrect. And then finally, what I had mentioned earlier, they used the natural log instead of raising it to the power where it's 10 to the negative, or excuse me, 10 to the 0.93, they used e raised to that power. So again, it's 10, not the base e from natural log. All right, well, let's go ahead and take a look at some more advice to help you avoid common mistakes. Remember to use the pKa value in the Henderson-Hasselbalch equation. So like I had mentioned earlier at the beginning of this video, you may be given the Kb value for a weak base. Then you have to find a way to convert the Kb into the Ka, and then take the negative log of the Ka to get the pKa value. Or, if you do take the negative log of Kb, then do 14 minus the pKb to get the pKa. So watch out for that. Now, if you are given a buffer solution that has equimolar amounts of a weak acid, Ha, and its conjugate base, A-, or if you're given a buffer with equimolar amounts of a weak base, B, and its conjugate acid, Hb+, then the pH of the buffer is equal to the pKa of the weak acid. Now, if the only change you make is to double the number of moles of each buffer component, the pH of that buffer would remain the same, but the buffer capacity would increase. And if you go in the opposite direction, if you reduce the number of moles of each buffer component by half, again, the pH of the buffer would remain the same, but the buffer capacity would decrease. Now, in an experiment involving buffers, talking about buffer capacity, in which a strong acid or a strong base is added to the solution with a greater buffer capacity will experience a smaller change in pH. On the other hand, the solution with a smaller buffer capacity will experience a greater change in pH. And then talking about topic 8.11, if you need to justify your answer regarding how the addition of a strong acid or a strong base will affect the solubility of a salt, then you should do the following for topic 8.11, pH and solubility. You should describe the details of how the concentrations of the aqueous ions in solution are affected when either a strong acid or a strong base is present. It may be helpful, or in some cases required, to write a net ionic equation to show what happens when a strong acid or a strong base is added to the mixture. It's also good to compare the values of the reaction quotient, Q, and the solubility product constant, KSP, and then definitely indicate the direction in which the equilibrium system will shift or proceed as a result of the change in concentration of certain aqueous ions. I put this in bold because this happened on the 2025 AP Chemistry exam, and I wanted to mention this to help you avoid this mistake. The undissolved solid in the mixture is not included in the KSP expression, and you will not earn the point for discussing a reaction that occurs between the aqueous hydronium ions from a strong acid and the undissolved solid present in the mixture. So, in light of that particular warning or piece of advice, here is an example of a free response question involving pH and solubility from the 2025 AP Chemistry exam. This is question 1, part F. Now, the dissolution of magnesium hydroxide was mentioned, and it said that the student adds nitric acid to decrease the pH. Does the amount of undissolved solid magnesium hydroxide increase, decrease, or remain the same as the nitric acid is added? Justify your answer. Now, if you're watching this video and thinking, that looks a lot like question 7, yes. I wrote question 7 based on that particular free response question from the 2025 AP Chemistry exam. So, nitric acid is added, the H+ ions from the nitric acid react with the hydroxide ions, hydroxide concentration decreases, Q becomes less than KSP, more solid magnesium hydroxide will dissolve, and the amount of undissolved magnesium hydroxide will decrease. You can see that's the official scoring guidelines answer. So what mistake am I helping you avoid making? Again, take a look at that first mistake. Students did not earn the point if they attributed the decrease in the amount of undissolved magnesium hydroxide to a direct reaction between the magnesium hydroxide solid and the added acid. So it's not the solid magnesium hydroxide that's reacting with the acid, it's going to be the aqueous hydroxide ions present in the solution. Again, that causes Q to become less than KSP. And then another mistake that students made is they did say that the acid reacts with the hydroxide, which is good, but then they didn't actually sufficiently discuss the resulting shift in the equilibrium position. Again, Q becomes less than KSP, the reaction will shift from left to right or from reactants to products, making the solid more soluble. So they said more magnesium hydroxide will dissolve because H+ reacts with OH-, but there wasn't a sufficient discussion of the resulting shift in the equilibrium position. All right, well, that wraps things up, so we have come to the end of this lesson. In my next lesson, I'll give you the chance to review and practice topics 9.1 to 9.3. If you enjoyed this lesson, I invite you to like this video and subscribe to my YouTube channel. Check out the links in the video description area, which include the link to my YouTube playlist organized by AP Chemistry CED units. You can add your comments and questions below this video, and you can also email me with your comments and questions at APChemistryReviewAndPractice@gmail.com. Thank you for letting me be your guide on the side as you strive toward that 5 on the AP Chemistry exam. Keep studying, and I'll see you next time on AP Chemistry Review and Practice.